Hi, and welcome to my Honours Degree Research presentation. My name is Marco, and I will be taking you through the research of our newly proposed machine learning algorithm, the Iterative Structure-Based Grammatical Evolution. This presentation will cover background literature and prior research, the proposed algorithm that addresses the gap in the existing literature, the methodology used to test the algorithm, results, and the final conclusion. As a start to previous research, we discuss genetic programming. GP is an evolutionary algorithm inspired by Darwin's theory of natural selection. Suppose we are trying to find a solution and there are multiple local optima in the search space. These local optima are solution representations that outperform any individuals in the surrounding search area. Individuals are typically represented as parse trees that can be executed to produce an output value. This output value is a measure of the individual's fitness or how well it solves the problem. In GP, individuals are initially randomly generated, since we don't know the positions of the optima, and distributed across the search space. For each generation, the genetic building blocks of the individuals undergo genetic operators, crossover, mutation, and selection, in order to shift the population towards an optima. As individuals evolve and grow more fit over generations, the population tends to converge towards an optima. This is a potential solution. The GP typically terminates when all individuals have converged around a certain solution, and that solution is returned as the GP's final result. However, often the solution found is a local optima and not a global optima. A global optima represents an ideal perfect solution to the problem, whereas a local optima is only a relatively good solution. This phenomenon is common in genetic programming and is known as premature convergence. For this initial spread of individuals, very few were gathered around the actual global optima. The population's tendency to gravitate towards the nearest solution instead of the best often results in premature convergence. As a remedy to this, we look at the Iterative Structure-Based Algorithm, or ISBA. This variation of GP states that the individuals in the search area localized around some optima will always have the same root trees, that is, the same nodes from the root node to some depth. As individuals move closer to the optima, the root trees grow deeper until all individuals have close to the exact same structure. The ISBA follows a two-step approach, in which the first phase is called a global search. This is typically a normal GP run until the individuals are identified to have a similar structure in their root trees. This indicates that the population is beginning to converge. Once the common root tree has been identified, it is fixed in the second step of the algorithm, the local search, in which only nodes below the root tree are evolved. These two steps are repeated until termination, but structural dissimilarity is enforced for each successive global and local search. This promotes exploration of the search space in the global search and exploitation in the local search. Finally, the best found solution is returned as the final output. As a demonstration, the first global search of the ISBA acts like a normal GP run, until majority of the individuals are identified to have structurally similar root trees. This indicates that the population is beginning to converge. The algorithm enters into the local search, fixing the common root tree and exploiting the local search space until the optima is converged to and found. The best result from the local search is saved, as well as the associated root tree. A new global search begins, and structural dissimilarity is enforced in the new individuals to prevent the previously found root tree from being converged to again. This forces the individuals to explore areas of the search space that has not been explored before. The global search continues until a new root tree is found, structurally dissimilar to any previously found root trees, in which the next local search is executed to quickly converge to the optima in that search space. This two-step approach continues, exploring various parts of the search space until the termination criteria is met, with the hopes of eventually finding a global optima. Once the ISBA terminates, the best found optima is returned as the final solution. Now we make a quick tangent to grammatical evolution, another variation of genetic programming aimed at addressing a different set of problems. In GE, we have a chromosome space acting as an interface to the program space. Every chromosome consists of a binary string, whereas programs are still parse trees. Chromosomes map to programs by pushing the binary string through a context-free grammar that generates a resulting parse tree. Searching and genetic operations occur in the chromosome space, however fitness evaluation still occurs on the produced parse trees. GE has a shorter runtime than GP due to the simple representation of binary strings. The context-free grammar allows GE to better define the syntax of individuals and constrain the search space to only include syntactically valid parse trees. Consequently, this results in quicker convergence to an optima. Despite these benefits, GE also suffers from premature convergence. Conducting a preliminary study, we ignored the structure of individuals in the program space and only observed convergence in the chromosome space. Consistent with convergence of individuals in GP, GE individuals in local search spaces centered around an optima would have prefixes in their chromosomes that were structurally similar to that of the optima. From this observation, we make a logical argument for the application of the ISBA to GE. The logical inference law of modus ponens states that if P implies Q and P is known to be true, then Q must also be true. In GP, the presence of the convergence pattern implied that an application of the ISBA would reduce premature convergence. From our preliminary study, we observed that the convergence pattern was indeed present in GE. Therefore, by modus ponens, we make the logical argument that the ISBA can be applied to the individuals in GE. From this assumption, we propose the Iterative Structure-Based Grammatical Evolution, or ISBGE, an application of the ISBA's foundational logic to the chromosomes of GE. The ISBGE follows the same two-phase approach of the ISBA, with the difference being that structural similarity is performed on the binary strings using common prefixes instead of a root tree. For the methodology followed in our practical development and testing of this algorithm, our objective was to test if the ISBGE successfully reduced premature convergence. This could be accomplished and verified by comparing its results to canonical GE. A lower best fitness produced by ISBGE over GE would suggest that the former succeeds at reducing premature convergence. The proof by demonstration methodology was followed, in which we iteratively developed and tested the algorithm. For extensive coverage in the ISBGE's performance comparison, we selected 3 functionally different benchmarks from an easy, intermediate, and difficult level: simple symbolic regression, heart disease classification, and the Tartarus problem, a notorious path-finding benchmark. To statistically verify our results, we ran a 2-sample hypothesis test on the mean best fitness scores produced by ISBGE and GE over 30 runs per benchmark. Taking a look at the results of some of our runs, we first observe a normal GE run in which premature convergence occurred sometime around generation 5000. The ISBGE, however, quickly detected convergence and sprouted into different areas of the search space, eventually finding a better solution than GE's local optima around generation 16000. From this graph, we can easily see the first global search succeeded by 2 local searches that were not very fruitful. However, on the second global search, enforcing structural dissimilarity in the root trees allowed the ISBGE to quickly find a solution that outperformed the local optima found by the first global search. In some of the initial runs, ISBGE did not always outperform GE, sometimes falsely assuming premature convergence earlier than its actual occurrence. However, continued parameter tuning and observation suggested that the ISBGE simply required more time in order to run more iterations of the global and local searching phases. This would allow it to explore more areas in the search space. Increasing the maximum amount of generations allowed the ISBGE to consistently outperform GE. Considering the experiment results as box plots, we observed that the mean best fitness score of ISBGE was lower than GE across all three benchmarks. Heart disease classification had the smallest difference, likely due to outliers in GE brought about by radical mutations or the stochastic element. The Tartarus problem represented the ideal behavior of ISBGE, where in worst case it would have the exact same best fitness as canonical GE. ISBGE's large interquartile range is explained by its tendency to explore more of the search space than GE, consequently producing more individuals with greatly varying fitnesses. From these final results, we observed the ISBGE to outperform GE on all three benchmarks. Finally, we rejected the null hypothesis on all three benchmarks using a 95% level of confidence. Considering the different categories covered by the benchmarks, we conclude with a 95% level of confidence that the ISBGE successfully reduces premature convergence.